Hi Year 8. So I want you to get your self-quizzing book out, okay? So this one here, your self-quizzing book, and you're also going to need your knowledge organizer wee booklet as well. So get those for me now, please. Now, if you turn to page 16, please, then we've got our self-quizzing questions for our heat topic starting. Now, you have been answering some of these in the retrieval roulettes that we've been doing in lessons, but instead of doing a retrieval roulette today, I want us to spend about 20 minutes doing these 3 pages. So page 16, 17 and 18. And I'll just take this opportunity to remind you about the process, okay? So it is described up here, but just in case, I'm going to run you through it again. So down here we have got a bunch of questions. Now remember, this number isn't just like the question number, because you'll notice they don't go in order, like it doesn't go from 1 to 10, okay? This number tells you where you get your answer in your knowledge organizer. So I'm going to talk you through even just getting this first one here. So the first question, write the definition for temperature. This tells me that I go to number 1 on my heat knowledge organizer. So I've got my knowledge organizer, it's the wee thin one, and I open it up until I find the heat page, and it's the second page here. And if we look here, number 1, temperature, gives us the definition of temperature. Now, one thing I do want to point out is that like if a question says number 11 on it, it doesn't mean you have to write all of this information here. You have to look in box 11 and find the answer that the question's talking about. I don't actually think that applies to any this week. So this week, if we look at the numbers, it's 1, 2, 3, 4, 5, 3, 2, 5, 6, 6, 7 and 8. So all of your answers for this week are going to come from this box up here. Okay, so I'll just remind you again what it is you need to do, and this will take about 20 minutes at least. So on your first page, so page 16, you look up your knowledge organizer, get the answers to these questions and write them in. Then spend a bit of time trying to learn off the answers, okay? Then get your knowledge organizer, hide it from yourself, turn this page, close it over, and now we're on page 17 and we cannot see page 16, okay? We've hidden that from ourselves. Then we try and answer this from memory. Now you're not going to get it all right, that's normal. So try and answer it from memory, then get a different coloured pen and either turn back to this, because you should have written this out perfectly from the knowledge organizer, and mark and correct your work, or you can just refer back to your knowledge organizer and check the answers off on it. And if you have it right, you mark it right. If you pretty much have it right, but there's maybe like 1 or 2 words missing, just write in the other words where they should go in the different colour. If there's one completely wrong, then you'll score it out and write in the correct answer that should go there, okay? Then spend a bit more time trying to get that information, particularly the information that you got wrong the first time. Get that right in your head. Then turn over to page 18. And you've got the same questions again, and this time again you're trying to answer from memory, and hopefully once you mark and correct it, you should have less of the different coloured pen on your page. Now, it doesn't have to be completely right by this stage, as long as you're correcting it and you're learning from what you're getting wrong, then that's brilliant. Now, if after you've done that, you still feel like, oh, there's some of those I'm not sure about, then that's what your workbook's for. You use your workbook to keep practicing these questions. So you could hide answers from yourself, like you can use another page, hide your answer space which you'll have written in, you've got your questions, and you can keep on practicing that in your workbook as long as you need. Okay? So that's what we're doing today instead of our retrieval roulette. This work here normally, remember, would be set as homework, but we're doing it in our lesson time today. Okay, so pause the video, get that done, and then restart the video for the rest of the lesson. Okay, so hopefully your self-quizzing went well and that's been a good way to get all that heat knowledge that we have been learning back in your head so you're ready, fresh to start today. So our information today is quite wordy, okay? So it says here, oh, by the way, I'm on page 55 in the notes. If you go turn in your notes to page 55, please. So you need to be able to describe the process of conduction in both conductors and insulators. So just a quick reminder, conduction, remember, is how heat energy is transferred through solid materials. If something is a conductor, that means it allows the heat energy to travel through it really, really quickly. And if something is an insulator, then the heat energy isn't going to travel through it very quickly at all. It will still, but it'll be a very, very slow process. Okay, now let's look here. In solids, you've maybe learnt about solids, liquids and gases in chemistry already. If so, happy days. But in a solid, all the atoms, so atoms are just the things that make up everything. They're held together really, really, really closely, and they're held together really tightly by chemical bonds. So the atoms themselves cannot move freely around within the solid. They have like we would call an equilibrium position, and that just means it's like their natural position. However, if you read this, the atoms can vibrate about their fixed position. So let's think about what that means. If you look around you, you're maybe working at a table, okay? See the table that's in front of you? Inside that, there's a bunch of wee tiny, tiny atoms. They do have a fixed position, but they'll all be vibrating around that position. So they'll all be there and they'll be vibrating around. They'll not vibrate the whole way over here or the whole way over here, but they will just be vibrating backwards and forwards about the same point. Now, what's really cool is that the hotter an object is, the more the object vibrates. Now let's think about that in terms of energy that we've been learning about this year. If an atom is hotter, then it has more heat energy, and whenever you have more energy, you're probably bouncing around the place. It's the same idea with the atoms. So whenever the atoms have more heat energy, they vibrate much more vigorously, is the word that we would use. So they start to vibrate a lot more. Now they're still in their fixed position, but they're wobbling around the place. Okay. Now, what else is cool is if we go the other way, if we cool something down and keep cooling it down, then the amount of heat energy that it has is getting less and less and less. So if our atoms are vibrating and then we cool it down, they start to vibrate slower and slower and slower and slower and slower. Eventually, they will stop vibrating, and the temperature that happens at is called absolute zero. And look, that's what it is, minus 273.15 degrees Celsius. I can't even imagine that degree of coldness. Yeah, so minus 273.15, and that is the coldest possible temperature that there is. It doesn't get any colder than that. So that is why it's called absolute zero. So absolute zero, it's not 0 degrees Celsius, because obviously we can get colder than that. It is minus 273.15 degrees Celsius, and it's actually called 0 Kelvin. So whenever you're a wee bit further up the school, you will start to use temperature being measured in Kelvin. For now, degrees Celsius is fine because it's what we're familiar with, okay? But it's just another temperature scale that we can use, and absolute zero would be 0 on the Kelvin scale. Okay, so that's a wee bit of extra information for you. So all atoms above absolute zero vibrate. As an atom increases in temperature, it gains energy and starts to vibrate more vigorously. The hotter an atom becomes, the more vigorously it vibrates. And this fact here is the key to the whole of the process of conduction in non-metals. So remember, non-metals are the insulators. They're the things that aren't very good at passing on heat energy. Okay, so if we look here, the information in this box is the information that you're going to have to learn. It's one of those things that you need to be able to describe really, really well. So I just want to talk you through what's going on in this diagram, okay? So this diagram here, these circles are the atoms inside a material. So this, remember, is our non-metals. In fact, you know what? That really should be labelled because it's not very clear there. That's a terrible job by me. So this is non-metals, if you write that in for me, please. Okay. So back to this, back to describing what it is. These circles here are the atoms. And again, I'm going to label them because they should be labelled. So atoms. Okay. And remember, they're just the things that make up everything, absolutely everything. This pen, this table, this page, my hand, everything made up of atoms. So each one of these is just drawn to represent an atom. If we supply heat at this end of our material, then these lines here are drawn to show that these atoms above the heat source are starting to vibrate much more vigorously. Okay, so if we're supplying heat to this one, then it's going to be gaining in heat energy and it's going to start wobbling all over the place. Now, whenever it does that, it's going to knock into this next one here. And whenever it does that, it actually passes some of its energy on to that one. So then this one starts to vibrate a little bit more. And then what do you reckon it's going to do? It's going to knock into its neighbouring particles and they're going to start to vibrate an awful lot more. And then that whole process slowly continues along the material. So I'll go through that one more time and then we'll read the wordy bit in your notes. So the atoms above the heat source are going to be getting extra heat energy. That's going to make them vibrate more vigorously than they already were, because remember, everything is vibrating a little bit inside. So these are going to start vibrating more vigorously. They're going to knock into the atoms beside them, pass on some heat energy, that's key, and then that makes them, these neighbouring particles or atoms, that makes them start to vibrate more vigorously. And then that whole process keeps on continuing. So these ones knock into these ones, which knock into these ones, which knock into these ones. Okay, and eventually the heat energy gets transferred along until, I think I talked about this in the very first heat lesson, but it's until everything really reaches the same temperature. Okay, so heat energy is always, or temperatures are always trying to like even themselves out. So these lines that I've drawn here, I'm just trying to represent that these ones are vibrating a lot. These ones are only vibrating a little bit because the heat energy hasn't reached there yet. Okay, so this here, important. The atoms above the heat source absorb heat energy. This makes them vibrate more vigorously and with greater amplitude. That just means going a bigger distance than their neighbouring particles. These vibrations pass from atom to atom through the solid structure, transferring heat in the form of kinetic energy as they do so. Because remember, kinetic energy is moving energy. So the more something's moving, the more kinetic energy it has. This process is slow, so it takes some time for the heat to transfer the full length of the insulator. Now, you'll notice some bits there are underlined. They tend to be the bits that get you marks in exams. So talking about the atoms above the heat source vibrating more vigorously and with greater amplitude, banging into their neighbouring particles and passing on the heat energy in the form of kinetic energy, that's what gets you the marks. But really, this is all what you're trying to say. You're trying to say this whole blurb, but I've underlined the very, very key points. Okay. Now, these, sorry, I've turned over the page there. These descriptions are going to come up in your self-quizzing booklet next week. Okay, so we will be spending a bit of time practicing that and rhyming it off and making sure that we can describe that in full. But for now, if you followed that okay, then we're going to start and go on to conduction in metals, which are the conductors. So if not, if you need to pause and have a wee another look through that and get your head around that, then do that and then restart the video when you're ready to look at metals. Okay, so over on to page 56. So the structure of metals differs slightly from non-metals. Okay, so in metals there are free electrons in the structure. So just to let you know what an electron is, it's part of an atom. An atom has a few different parts in it. It has these things called protons and neutrons, and they're held inside the nucleus of the atom. So it's like the wee core of the atom. So if my hand's here, in fact, if my mouse, if I hold my mouse, this is my nucleus of my atom. Inside here are protons and neutrons. Electrons are little things that orbit around the outside. They're still part of the atom, but they're orbiting around the outside. Now, again, you've maybe learnt about that in chemistry. If you haven't, you will at some stage. And in fact, we'll talk about it a little bit more whenever we're doing static electricity. Okay, so where am I? Yeah, so in metals, what actually happens is that some of those electrons from the atoms aren't connected to the atoms anymore. They're like free to roam around the place, and they actually end up speeding up the process of conduction in metals. So in metals, there are free electrons in the structure. So these are electrons which have escaped from atoms. Now, technically that means the atoms are no longer atoms. They're actually now called ions. For now, we will not get too bogged down in that. Now, in my description here, I have used the word ions. If you use the word atom at this stage, we'll probably let you away with it. But if you can, try and get into the habit of, in metals, calling them ions, because they don't have all their electrons anymore. Okay, so where am I? These are electrons which have escaped from atoms and can move freely throughout the solid. It's these free electrons that make metals such good conductors of heat. So let's look at this diagram for metals, and again, let's label it. So label this as metals. So it's a very, very similar diagram to the last one. So we still have our, well, I was going to say our atoms, I'm going to say ions. Okay, the circles. But we have these little bits here, and these wee dots I've just drawn to represent the free electrons. So it's the same idea, but with an extra wee bit. So we've got our heat source at this end. We've got our ions above the heat source. They gain the extra energy, vibrate more vigorously, knock into their neighbouring particles. They make them vibrate more vigorously, and they keep passing on heat energy. Really, it's in the form of kinetic energy, but you can say either there. So they keep passing on heat energy down this solid the exact same way as we've just described happening in non-metals. So that process still happens, but there's this little extra bit here. So these wee dots here are the free electrons. Now they are tiny. Look at all the size of that compared to the atoms. Or the ions, the ions. And do you know what? In no way have I drawn that in any way to scale. The electrons would be much, much tinier if that was the size of the atom. So if this wee tiny wee electron gets a bunch of heat energy from this heat source, it's going to make it go wild. So this wee electron is going to end up being able to like whiz around the place inside the metal. So it's gained all the heat energy, but it might actually end up knocking into an ion over here, passing on the heat energy that way and getting this one vibrating, which is then going to be able to pass on to all the other ones. So do you see how the wee tiny electrons actually make the whole process speed up a lot more? Because they're so tiny, that gain in energy has a bigger effect on them, and then they're able to whiz all around the place and pass on heat energy to other ions, and then they're able to keep on doing their job. So hopefully what I've said there has made sense. I'm going to read through the little description in your notes. So in metals, both the ions and the free electrons above the heat source absorb heat energy. The same process happens, can't read. So the same process happens with the ions as did with the atoms in non-metals. But because the free electrons have also gained energy, this allows them to move much faster than before. As they move through the metal, free electrons collide with the metal ions. In these collisions, the free electrons give some of their kinetic energy to the metal ions and cause them to vibrate with greater amplitude than before. Free electron conduction is much, much faster than conduction caused by vibrations passing from atom to atom. So materials with free electrons, which is all metals, are the best conductors of heat energy. Okay, so same idea with the last one. This here is like the full description. The underlined bits are the really, really, really important bits that get you marks. But obviously, if you just wrote the words that were underlined, it wouldn't make sense. You have to put it into proper sentences. But they are the key bits of information. Okay, so again, pause. Make sure you've got that into your head and you can follow what's going on there before moving on to the next wee bit. Okay, I'm on to page 57 here. Now, this is a really cool little demonstration. I actually really like doing it in school and getting you to touch the what do you call it, the test tube, and feeling the ice at the bottom. Unfortunately, I'm not able to do that. So at the end, I'm going to link a video to an experiment of someone else carrying this one out. Okay. Now, anyway, so these processes, those processes that we have just explained, how conduction happens in solids, in the non-metals and in the metals, can help explain why liquids are poor conductors of thermal energy. Because if you think back to the first thing we said about how conduction happens, the particles need to be really, really pressed like quite close together, because then this one starts to vibrate and knocks into this one, and so on. In liquids, the particles are more spread out than each other, so that's not going to happen. And very, very few liquids have free electrons. Okay, so most liquids have no free electrons and so rely on atom to atom vibrations. But because atoms in a liquid are constantly moving, they don't have that fixed position that the electron or that the atoms in the solids have. Conduction doesn't really happen in an orderly way, right? So that's why liquids are poor conductors. Their particles are too spread out and they don't have the free electrons. Now, liquid metals are an exception to this rule. So at room temperature, I'm sure you've heard of mercury, which used to be used in thermometers. It's a liquid at room temperature, but it's still a metal. So it conducts using its free electrons. Now, this little demonstration here is really good at showing why, or showing that, I suppose I should say. It's good at showing that water is a really, really poor conductor. So what we do is we get a block of ice and we put it in a wee test tube of water. Now, ice floats on water, so this weight is put in to hold the ice down at the bottom of the test tube. Then we take a Bunsen burner and we heat up the water at the top, and what we actually find is the water at the top can be boiling. You can see that it's bubbling away, it's like boiling water, but the ice at the bottom is still frozen. So this is a good wee demonstration to show that liquids, water, are poor conductors. They are not good at conducting heat energy. So if the water at the top here is boiling, think about what temperature that is, 100 degrees Celsius. But that heat energy hasn't been able to transfer down to this ice cube to melt it because it's still frozen. So this is really, really good at showing or demonstrating that water is a poor conductor. Okay, so I need you to try and answer these. Why is the weight needed, and how does this show that water is a poor conductor? So I have basically told you the answers there. We'll see if you were listening. And I am going to link a video of this experiment here. So if you click on that, then you'll be able to see the experiment happening. But that is us for today. A lot of new information to take in there, Year 8. I'll see you next week. Okay, bye.